Deep beneath Jupiter's swirling clouds, where crushing pressure should destroy any organized structure, the Juno spacecraft has discovered something that really defies the laws of planetary science. April 18, 2024, marked the day our understanding of gas giants was turned upside down, when Juno's instruments penetrated deeper than ever before and found a massive organized storm system thriving in conditions that should be, well, impossible. This terrifying discovery beneath Jupiter's surface has forced scientists to question everything they thought they knew about how giant planets work and what secrets they're hiding in their depths. The mysterious central storm discovery. Buried beneath Jupiter's great red spot lies something that has left planetary scientists, honestly, speechless. Juno's microwave radiometer, capable of penetrating hundreds of kilometers below the visible cloud layers, revealed a massive cyclonic structure extending far deeper than any storm system should theoretically survive. Scott Bolton, Juno's principal investigator at the Southwest Research Institute, described the discovery as completely unprecedented in planetary science. The hidden storm system spans approximately 3,000 kilometers in diameter and extends at least 500 kilometers below Jupiter's ammonia cloud deck, depths where the crushing pressure should have destroyed any organized weather pattern. Unlike surface storms that dissipate when they lose energy, this deep structure appears to be feeding off Jupiter's internal heat source, creating a perpetual motion system that may have existed for centuries or even millennia. The discovery really challenges fundamental assumptions about atmospheric dynamics on gas giant planets. Traditional models predicted that Jupiter's atmosphere would become increasingly uniform with depth, but Juno's data reveals complex, organized structures persisting in regions where chaos should reign supreme. This finding suggests Jupiter's interior is far more dynamic and mysterious than anyone imagined. The beginning of the mission. August 5, 2011 marked the beginning of humanity's most ambitious journey to Jupiter, when Juno launched from Cape Canaveral, aboard an Atlas V rocket. The mission was conceived by Scott Bolton and his team to answer fundamental questions about Jupiter's formation, composition, and internal structure that had puzzled scientists for decades. Unlike previous Jupiter missions that conducted brief flybys, Juno was designed for an extended orbital campaign using a highly elliptical 53.5-day orbit that would repeatedly dive close to the planet's cloud tops. The spacecraft carried 9 sophisticated instruments, including a gravity science experiment that would map Jupiter's interior mass distribution with, honestly, unprecedented precision. Juno's journey required a complex 5-year trajectory, including a crucial Earth flyby in October 2013, to gain the velocity needed to reach Jupiter. The mission faced numerous technical challenges, including designing electronics capable of surviving Jupiter's intense radiation environment, radiation levels that would kill an unprotected human in minutes. NASA engineers had to shield Juno's sensitive instruments inside a titanium vault to prevent radiation damage during the planned 37 orbital passes around the gas giant. Jupiter is the world of chaos. Jupiter's atmosphere represents controlled chaos on a scale that just dwarfs anything found elsewhere in the solar system. Juno's JunoCam and infrared instruments revealed that Jupiter's iconic bands and zones are far more turbulent and violent than telescopic observations from Earth had suggested. Wind speeds reach 640 kilometers per hour at the equator, driven by the planet's rapid 9.9-hour rotation period that creates the fastest day of any planet in our solar system. The atmospheric bands aren't static features but dynamic rivers of gas flowing in opposite directions, creating massive shear zones where adjacent streams collide and generate enormous cyclonic storms. Candace Hansen-Koharchek, who leads JunoCam operations at the Planetary Science Institute, described Jupiter's weather as organized chaos, where small disturbances can cascade into great red spot-sized storms within weeks. The planet's atmosphere extends thousands of kilometers deep, gradually transitioning from gas to liquid hydrogen under increasing pressure and temperature. Juno's microwave radiometer detected ammonia concentrations varying dramatically with depth and latitude, suggesting complex convection patterns that transport material between atmospheric layers. This chaotic mixing prevents Jupiter from achieving thermal equilibrium, maintaining the temperature and pressure gradients that drive its perpetual storm systems across the planet's entire hemisphere. Io, the volcanic moon. Io, Jupiter's innermost large moon, represents the most volcanically active world in the solar system, with over 400 active volcanoes spewing sulfur compounds hundreds of kilometers into space. Juno's extended mission has provided, honestly, just unprecedented views of Io's volcanic activity, revealing eruptions that, really dwarf anything on Earth. The moon's extreme volcanism results from tidal heating caused by Jupiter's immense gravitational pull and orbital resonances with Europa and Ganymede. As Io orbits Jupiter every 1.77 days, these gravitational forces flex and stretch the moon's interior, generating enough heat to keep its core molten despite its small size. Alessandro Mura, from Italy's National Institute for Astrophysics, used Juno's infrared spectrometer to track individual volcanic plumes, and discovered that some eruptions reach temperatures exceeding 1,800 degrees Celsius, hot enough to melt rock instantaneously. The volcanic activity continuously resurfaces Io, making it the youngest-looking world in the solar system with no impact craters visible on its sulfur-painted surface. Io's volcanism also feeds Jupiter's radiation belts, creating a plasma torus of charged particles that contributes to the planet's deadly radiation environment that threatens any spacecraft venturing too close. Research on Jupiter's magnetic field. Jupiter possesses the most powerful magnetic field in the solar system, extending millions of kilometers into space and trapping deadly radiation that would be lethal to unprotected astronauts. Juno's magnetometer, led by Jack Connerly from NASA Goddard Space Flight Center, revealed that Jupiter's magnetic field is far more complex and honestly chaotic than Earth's relatively orderly dipolar field. The magnetic field strength reaches 4.3 Gauss at Jupiter's cloud tops, 10 times stronger than Earth's field, and is generated by electrical currents flowing through the planet's metallic hydrogen core. Unlike Earth's magnetic field, which has clear north and south poles, Jupiter's field shows irregular patterns with multiple magnetic anomalies scattered across its surface. The field appears to be generated by convection in Jupiter's outer core, where liquid metallic hydrogen acts as an electrical conductor under extreme pressure and temperature conditions. Juno's measurements revealed that the magnetic field varies significantly between different regions of the planet, suggesting complex dynamics within Jupiter's deep interior. The magnetic field creates Jupiter's enormous magnetosphere, which extends beyond the orbit of Saturn and acts as a natural particle accelerator, energizing charged particles to deadly levels that pose serious radiation hazards to spacecraft and future human exploration missions. Juno mission peaks under Jupiter's surface. Juno's gravity science experiment has, really revolutionized our understanding of Jupiter's internal structure by measuring tiny variations in the spacecraft's orbital velocity as it passes over different regions of the planet. Luciano Ies, from Sapienza University of Rome, led the gravity investigation that revealed Jupiter's core is not the solid, well-defined sphere that scientists expected, but rather a fuzzy or dilute core extending halfway to the planet's surface. The core appears to be partially dissolved, mixed with surrounding metallic hydrogen, in a way that creates a gradual transition rather than a sharp boundary. This discovery suggests that Jupiter experienced a giant impact early in its formation that disrupted its original core structure. The gravity measurements also revealed that Jupiter's atmospheric bands extend 3,000 kilometers deep into the planet, much deeper than theoretical models predicted. Yohai Kaspi from the Weizmann Institute of Science used Juno's gravity data to create three-dimensional maps showing how mass is distributed within Jupiter's interior. These measurements required extraordinary precision, detecting changes in Juno's velocity as small as 0.01 millimeters per second, equivalent to measuring the speed of a growing human fingernail from millions of kilometers away. Jupiter's formation and composition. Jupiter's formation story has been, completely rewritten based on Juno's discoveries about the planet's internal structure and composition. The traditional core accretion model suggested Jupiter formed when a solid core of rock and ice grew large enough to gravitationally capture the surrounding solar nebula gas. However, Juno's detection of a dilute core suggests a more violent formation process, involving planetary collisions that disrupted the original solid core. Tristan Guillot from the Côte d'Azur Observatory actually proposed that Jupiter may have experienced multiple giant impacts during its early formation, including collisions with Earth-sized protoplanets that scattered core material throughout the interior. The planet's composition reveals it contains between 2 and 4 times more heavy elements than the Sun, indicating Jupiter formed from materials enriched in rocks and metals beyond simple gas capture. Juno's measurements show that Jupiter's atmosphere contains water vapor at concentrations of 0.25%, which is 3 times more than previously detected, suggesting the planet formed farther from the Sun, where water ice was abundant. And the discovery of ammonia and hydrogen sulfide at varying depths indicates complex chemical processes occurring within Jupiter's interior, where extreme pressure and temperature create conditions unlike anywhere else in the solar system. Jupiter as Earth's protector. Jupiter serves as our solar system's cosmic vacuum cleaner, using its immense gravitational field to capture or deflect potentially dangerous asteroids and comets that might otherwise threaten Earth. With a mass 318 times greater than Earth's, Jupiter's gravity dominates the outer solar system and has fundamentally shaped the architecture of our planetary neighborhood. Kevin Grazier, a planetary scientist who has studied Jupiter's protective role, estimates that Jupiter reduces the impact rate of long-period comets on Earth by a factor of 1,000. The planet's gravitational influence created the Kirkwood gaps in the asteroid belt, regions where asteroids just can't maintain stable orbits due to resonances with Jupiter's 11.8-year orbital period. However, Jupiter's protection isn't absolute. The same gravitational forces that deflect some objects can also redirect others toward the inner solar system. The Shoemaker-Levy 9 comet impact back in 1994 really demonstrated Jupiter's role as a cosmic target, absorbing impacts that might otherwise threaten terrestrial planets. Juno's extended observations have revealed how Jupiter's magnetosphere interacts with the solar wind, creating a protective bubble that helps shield the inner solar system from high-energy cosmic radiation that could affect planetary atmospheres and potentially harm life. The Great Red Spot Mystery. The Great Red Spot, Jupiter's most famous feature, has been continuously observed for over 350 years, making it the longest-lived storm system known in the solar system. Juno's close-up observations revealed that this massive anticyclone extends approximately 300 kilometers below Jupiter's cloud tops and reaches temperatures of -160 degrees Celsius at its summit. Amy Simon from NASA Goddard Space Flight Center has tracked the Great Red Spot's gradual shrinkage over the past century. The storm has decreased from 40,000 kilometers wide in the 1800s to approximately 16,000 kilometers today. Juno's microwave radiometer detected that the Great Red Spot is deeply rooted in Jupiter's atmosphere, functioning as a high-pressure system that rotates counterclockwise every 6 Earth days. The storm's iconic red coloration likely results from phosphorus compounds and other chemicals brought up from Jupiter's deeper atmospheric layers through powerful convection currents. Gerald Eichstadt, a citizen scientist working with JunoCam data, has created detailed maps showing how the Great Red Spot interacts with surrounding cloud bands and smaller storm systems. The storm's longevity results from Jupiter's lack of solid surface features or continents that would disrupt its circulation patterns, allowing it to persist indefinitely in the planet's fluid atmosphere. Jupiter's deep atmospheric layers. Beneath Jupiter's visible cloud decks lies a complex atmospheric structure that extends thousands of kilometers into the planet's interior, gradually transitioning from gas to liquid under increasing pressure. Juno's microwave radiometer has penetrated deeper into Jupiter's atmosphere than any previous instrument, revealing ammonia concentrations that vary dramatically with depth and latitude in patterns that really defy simple atmospheric models. Chung Lee from the University of California, Berkeley discovered that ammonia becomes depleted at certain depths, suggesting complex chemical processes and circulation patterns that transport materials between atmospheric layers. The atmospheric layers include distinct regions: the upper troposphere where visible clouds form, the deeper stratosphere where temperatures increase with altitude, and the thermosphere where solar radiation heats the thin gas to over 1,000 degrees Celsius. Lee Fletcher from the University of Leicester used Juno's infrared observations to map temperature variations that reveal convection cells extending hundreds of kilometers below the cloud tops. The deep atmosphere shows evidence of phosphine gas, carbon monoxide, and methane that really shouldn't exist at those depths according to chemical equilibrium models. These discoveries suggest that Jupiter's deep atmosphere is actively mixed by powerful convection currents that transport chemicals from the hot interior to the cold upper atmosphere, creating a dynamic system that continues to challenge our understanding of giant planet atmospheric dynamics. Juno's deep scan of Jupiter has revealed a world far more complex and mysterious than anyone imagined. From the dilute core that defies formation theories to the organized storm systems lurking beneath the clouds, Jupiter continues surprising scientists with each new discovery. The gas giant's protective role in our solar system and its extreme atmospheric dynamics make it both fascinating and honestly, kind of terrifying. These revelations prove that even after centuries of observation, Jupiter still holds secrets that could reshape our understanding of planetary science. Subscribe to Stellar Tech for more incredible discoveries from the frontiers of space exploration. When astronomers discovered Oumuamua in 2017, they thought they'd found a typical interstellar visitor, just a chunk of rock from another star system passing through our cosmic neighborhood. But, 7 years later, the more we learn about interstellar objects, the stranger Oumuamua becomes. The recent discovery of 2I-Borisov and now 3I-ATLAS has given scientists a baseline for what normal interstellar objects should look like. The problem? Oumuamua doesn't match the pattern at all. Today we're exploring how new interstellar discoveries are making our first cosmic visitor look increasingly alien and mysterious.
The discovery of 3I-ATLAS.
January 2025 marked a milestone in astronomy, when the ATLAS asteroid survey detected what appeared to be a routine asteroid, designated C2023A3. However, months of orbital analysis revealed something extraordinary. This wasn't a solar system object at all, but our third confirmed visitor from interstellar space. Larry Deneau, principal investigator of the ATLAS project at the University of Hawaii, initially dismissed the object as typical space debris until precise astrometry revealed its hyperbolic trajectory. Unlike Oumuamua's mysterious behavior, 3I-ATLAS behaved exactly as astronomers expected an interstellar comet should. As it approached the Sun, the object developed a classic comet tail, began outgassing water vapor and carbon monoxide, and showed predictable brightness variations consistent with a rotating, icy nucleus. Robert Warwick, the same astronomer who discovered Oumuamua with the Pan-STARRS telescope, confirmed that 3I-ATLAS displayed all the characteristics absent from our first interstellar visitor. The object's composition matched theoretical predictions for comets formed in other star systems, with spectroscopic analysis revealing familiar water ice, carbon dioxide, and rocky material. This normal behavior made Oumuamua's anomalies even more puzzling and significant. The Oumuamua discovery. October 19, 2017, changed our understanding of the cosmos, when Pan-STARRS 1 telescope in Hawaii detected a fast-moving object unlike anything seen before. Robert Warwick was conducting routine asteroid observations when he noticed an object moving too quickly to be bound by the sun's gravity. Initially catalogued as C2017U1, then reclassified as A2017U1, when no comet tail appeared, the object finally received the designation 1I/Oumuamua, the first confirmed interstellar visitor to our solar system. The Hawaiian name means scout or messenger from afar, chosen by the Pan-STARRS team to honor its discovery location. Oumuamua was already leaving the solar system when detected, having made its closest approach to the Sun weeks earlier. The object's discovery timeline was incredibly tight. Astronomers had only a few weeks to observe it before it faded beyond detection limits. European Southern Observatory's Very Large Telescope and other major observatories worldwide immediately began tracking campaigns. The International Astronomical Union had to create an entirely new designation system for interstellar objects, with the I prefix distinguishing visitors from other star systems from ordinary asteroids and comets born in our solar system. Oumuamua's strange properties. Oumuamua defied every expectation astronomers had about interstellar objects through its bizarre physical characteristics and behavior. The object measured approximately 400 meters long and only 40 meters wide, creating an unprecedented 10-to-1 aspect ratio that made it the most elongated object ever observed in space. Alan Fitzsimmons from Queen's University Belfast led spectroscopic studies revealing that Oumuamua's surface was dark reddish in color, similar to objects in the outer solar system that have been irradiated by cosmic rays for millions of years. The object rotated every 7.3 hours, creating dramatic brightness variations as different faces reflected varying amounts of sunlight toward Earth. Unlike typical asteroids or comets, Oumuamua showed no signs of outgassing, dust production, or tail formation, despite passing close to the Sun, where volatile materials should have vaporized. Marco Michelli from the European Space Agency discovered that the object was gradually accelerating away from the Sun, behavior that suggested comet-like outgassing but without any visible evidence of gas or dust emission. Temperature modeling indicated that Oumuamua's surface should have been hot enough to sublimate water ice, yet no outgassing was detected by even the most sensitive instruments available to astronomers worldwide.
The acceleration mystery.
The most perplexing aspect of Oumuamua emerged when precise astrometric measurements revealed the object was accelerating away from the sun without any visible mechanism to explain this behavior. Marco Michelli and his team at the European Space Agency used Hubble Space Telescope observations combined with ground-based tracking data to determine that Oumuamua was experiencing a small but measurable non-gravitational acceleration. The acceleration was approximately 100,000th of a meter per second squared, tiny, but significant enough to affect the object's trajectory over time. For typical comets, this type of acceleration results from the rocket effect of outgassing materials as solar heating vaporizes ice and other volatiles from the nucleus. However, Oumuamua showed absolutely no signs of outgassing, dust production, or comet tail formation that would account for the observed acceleration. Davide Farnokia from NASA's Jet Propulsion Laboratory confirmed that the acceleration was real and not an artifact of observational error or gravitational perturbations from known solar system bodies. The mystery deepened when astronomers realized that the acceleration was decreasing as Oumuamua moved farther from the sun, exactly matching the pattern expected from solar-powered outgassing, but without any detectable outgassing occurring.
Scientific investigations.
NASA's Spitzer Space Telescope conducted crucial observations that, honestly, deepened the Oumuamua mystery rather than solving it. Davide Farnokia led the Spitzer investigation, searching for any infrared signature that might indicate outgassing or thermal emission from the object's surface. The results were shocking. Spitzer detected no thermal emission whatsoever, suggesting Oumuamua's surface was either extremely small or highly reflective. The albedo measurements indicated that Oumuamua reflected approximately 10 times more sunlight than typical asteroids, giving it an unusually bright mirror-like surface. Alan Harris from the German Aerospace Center collaborated on thermal modeling that revealed Oumuamua must be either much smaller than initially estimated or composed of highly reflective material, unlike any known solar system object. The James Webb Space Telescope was unfortunately not yet operational during Oumuamua's passage, but ground-based spectroscopy by teams led by Alan Fitzsimmons revealed a surface composition that appeared similar to organic-rich asteroids from the outer solar system. However, the complete absence of water vapor, carbon monoxide, or dust emission remained unexplained by any conventional model of interstellar object composition and behavior.
The alien hypothesis.
Abraham Loeb, chair of Harvard University's astronomy department, sparked worldwide controversy by proposing that Oumuamua might be an artificial object created by extraterrestrial intelligence. In his analysis published in astrophysical journal Letters with Shmuel Bialy, Loeb suggested that Oumuamua's unusual acceleration could be explained if it were a light sail, an ultra-thin sheet of material propelled by solar radiation pressure. The hypothesis proposed that Oumuamua might be debris from alien technology, possibly a defunct probe or even a deliberately sent investigation device from another civilization. Loeb calculated that a sail-like object only millimeters thick but hundreds of meters wide could experience exactly the type of acceleration observed without requiring outgassing. The artificial origin theory gained traction when Loeb noted that Oumuamua's extreme elongation and high reflectivity were consistent with constructed materials rather than natural rock or ice. NASA's reaction was skeptical but respectful, with Thomas Zurbuchen, former associate administrator for science missions, acknowledging that extraordinary claims required extraordinary evidence but shouldn't be dismissed without investigation. Loeb's hypothesis divided the scientific community, with many astronomers arguing that natural explanations should be exhausted before considering extraterrestrial origins for unusual but not impossible celestial phenomena.
The dark comet theory.
Darrell Seligman from the University of Chicago and Gregory Laughlin from Yale University proposed a natural explanation for Oumuamua's mysterious behavior through their innovative dark comet hypothesis. Their theory suggested that Oumuamua was composed primarily of hydrogen ice, frozen molecular hydrogen that would be invisible to most telescopes and leave no detectable outgassing signature. Hydrogen ice sublimates at extremely low temperatures, and produces gas that's nearly impossible to detect with conventional instruments, potentially explaining the acceleration without visible outgassing. The theory required Oumuamua to have formed in an exceptionally cold environment, possibly in the outer regions of another star system where temperatures were low enough for hydrogen to freeze solid. Seligman calculated that objects composed of hydrogen ice could maintain their integrity during interstellar travel, and would begin sublimating as they approached any star, producing the rocket-like acceleration observed. The hydrogen ice hypothesis gained support from theoretical models, showing that such objects could form naturally in protoplanetary disks under specific conditions. However, the theory faced criticism because hydrogen ice has never been observed in space, and would require extraordinary preservation during Oumuamua's millions of years journey through interstellar space before reaching our solar system.
The ongoing debate.
Abraham Loeb remained unconvinced by the dark comet theory, publishing detailed critiques arguing that the hydrogen ice hypothesis created more problems than it solved. In his book Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, Loeb pointed out that hydrogen ice would require formation temperatures of -434 degrees Fahrenheit, colder than most regions of interstellar space. He argued that such an object would likely sublimate completely during its journey to our solar system, making survival impossible over the millions of years required for interstellar travel. Darrell Seligman responded with refined calculations showing that sufficiently large hydrogen ice objects could retain enough material to remain intact, but acknowledged the theory required exceptional formation conditions. The scientific community remained divided, with most astronomers favoring natural explanations, while acknowledging the limitations of current observational data. European Southern Observatory astronomers conducted follow-up studies of other interstellar objects, finding that normal comets like 2I-Borisov behaved exactly as traditional comet models predicted, making Oumuamua's anomalies even more striking. The debate highlighted fundamental gaps in our understanding of interstellar object formation and composition that persist today.
Project Lyra mission concept.
Andreas Hein from the Initiative for Interstellar Studies and Zach Manchester from Stanford University developed Project Lyra, an ambitious mission concept designed to intercept and study Oumuamua before it disappears forever into interstellar space. The proposed mission would require launching by 2025 to have any chance of reaching the object, using Jupiter and possibly Saturn for gravitational assists to achieve the enormous velocity needed. ESA's Advanced Studies program examined the technical feasibility, concluding that a small CubeSat could theoretically reach Oumuamua by 2054 if launched on a powerful rocket like NASA's SLS or SpaceX's Falcon Heavy. The mission would carry miniaturized instruments including cameras, spectrometers, and possibly a penetrator to sample the object's interior composition. Project Lyra faces enormous technical challenges, including the need for spacecraft to survive decades in space while maintaining operational capability upon arrival. The mission cost estimates range from $500 million to several $billion, making it financially challenging for most space agencies. Despite these obstacles, Project Lyra represents humanity's best chance to definitively determine Oumuamua's true nature and resolve the debate between natural and artificial origins that has captivated both scientists and the public worldwide.
The future hunt.
The Vera C. Rubin Observatory, beginning operations in 2025, promises to revolutionize our ability to detect and study interstellar visitors before they leave the solar system. Mario Jurek from the University of Washington leads the legacy survey of space and time that will discover an estimated 1 interstellar object per year, a dramatic increase from our current rate of discovery. The observatory's wide-field camera and rapid survey capabilities will provide weeks or months of advance warning when interstellar objects approach, allowing detailed study missions to be planned and executed. NASA's Interstellar Probe mission, currently in development, could potentially encounter interstellar objects during its journey beyond the solar system. The comparison between Oumuamua 2I-Borisov and 3I-ATLAS has already revealed that our first visitor was genuinely anomalous, rather than representative of typical interstellar objects. As we discover more interstellar visitors, the statistical sample will help determine whether Oumuamua was a rare natural phenomenon or something more extraordinary. The scientific consensus suggests that while artificial origins remain possible, natural explanations involving exotic compositions or formation mechanisms are more likely. However, the mystery of Oumuamua has permanently changed how astronomers approach the study of interstellar objects and the search for potential technosignatures in space. Oumuamua arrived as a mysterious messenger from another star system and left as one of astronomy's greatest unsolved puzzles. The discovery of normal interstellar objects like 2I-Borisov and 3I-ATLAS has only made our first visitor appear more anomalous and extraordinary. Whether it was exotic hydrogen ice, alien technology, or something we haven't yet imagined, Oumuamua proved that the universe still holds surprises that challenge our understanding. Subscribe to Stellar Tech for more cosmic mysteries that push the boundaries of science and keep us wondering what else might be traveling between the stars. September 26, 2022 changed everything we thought we knew about asteroid defense. NASA's DART spacecraft slammed into Dimorphos, a small asteroid moon orbiting the larger Didymos, in humanity's first attempt to deliberately alter a celestial object's path. The mission was supposed to be a simple test: hit the target, measure the orbital change, and prove we could defend Earth from asteroid threats. But what happened next stunned scientists worldwide. The impact didn't just nudge Dimorphos off course, it unleashed something completely unexpected that's still reshaping our understanding of asteroids today. The kamikaze mission DART, Double Asteroid Redirection Test, represented humanity's first planetary defense experiment, designed by NASA's Planetary Defense Coordination Office under the leadership of Lyndon Johnson. The $325 million spacecraft launched on November 24, 2021, beginning a 10-month journey to intercept Dimorphos, a 525-foot-wide moonlet orbiting the larger asteroid Didymos. The mission's objective was elegantly simple yet technically challenging: crash into Dimorphos at 14,000 miles per hour, and measure how much the impact changed its orbital period around Didymos. DART carried no scientific instruments for studying the asteroids. It was purely a kinetic impactor, essentially a guided missile designed to test whether humanity could deflect a potentially hazardous asteroid. The spacecraft used ion propulsion and autonomous navigation systems to home in on its target with pinpoint accuracy. Mission controllers at Johns Hopkins Applied Physics Laboratory in Maryland could only watch as DART approached its target. Since the 7 million mile distance meant radio signals took several minutes to travel between Earth and the spacecraft. The final approach relied entirely on DART's onboard camera and navigation system to guide it to impact. Perfect impact. At exactly 7:14 p.m. Eastern Daylight Time on September 26, 2022, DART achieved what many considered impossible: a direct hit on a target the size of a football stadium from millions of miles away. The impact occurred with the force of several tons of TNT, creating a spectacular explosion visible to ground-based telescopes worldwide. Andy Rivkin, the mission's investigation team lead at Johns Hopkins Applied Physics Laboratory, confirmed that DART struck within 17 meters of Dimorphos's center, a bullseye by any measure. The impact was captured by DART's own camera in its final moments, showing the rocky, boulder-strewn surface of Dimorphos rushing toward the spacecraft at incredible speed. Simultaneously, LISIACube, a small Italian-built observer spacecraft, photographed the collision from a safe distance, capturing images of the impact plume and debris cloud. Telescopes on Earth, including the Hubble Space Telescope and James Webb Space Telescope, immediately began tracking the aftermath. The impact created a massive debris tail stretching thousands of miles behind Dimorphos, visible as a bright streak against the darkness of space. Initial observations confirmed the mission was an immediate success, but the real surprises were just beginning to unfold. The shocking results. The impact results exceeded all expectations in ways that left scientists scrambling to understand what had happened. Pre-mission calculations predicted DART would shorten Dimorphos's orbital period around Didymos by approximately 10 minutes. Instead, measurements revealed the orbital period had decreased by 32 minutes, more than 3 times the predicted change. Tom Statler, NASA's DART program scientist, called the results remarkable and far beyond their most optimistic projections. The massive orbital shift suggested Dimorphos was much less dense than anticipated, behaving more like a loose pile of rubble than a solid rock. Andy Cheng, the DART investigation team co-lead, explained that the enhanced momentum transfer indicated the asteroid was essentially a rubble pile held together primarily by its own weak gravity. The impact had not only displaced material from the collision point but also triggered a cascade effect where ejected debris contributed additional momentum change. This discovery revolutionized our understanding of small asteroids. Many are apparently fragile, loosely bound collections of rocks and dust rather than solid objects. The finding has profound implications for future asteroid deflection missions, suggesting smaller impactors might be far more effective than previously thought. The debris mystery. Months after impact, Dimorphos continued surprising scientists with its ongoing transformation. Hubble Space Telescope observations revealed that the asteroid was still ejecting material long after the collision, creating multiple debris tails that evolved and changed direction over time. John Yang Lee from the Planetary Science Institute led analysis showing Dimorphos had developed at least 3 distinct debris tails spreading in different directions. The continued material ejection suggested the impact had fundamentally destabilized the asteroid's structure, causing ongoing landslides and surface collapse events. Christina Thomas from Northern Arizona University reported that Dimorphos was losing mass at a rate much higher than expected, with debris continuing to stream away from the impact site months later. Some debris particles were moving fast enough to escape Dimorphos's weak gravitational field permanently, while others were falling back to the surface in slow motion. The European Space Agency's upcoming Hera mission, scheduled to arrive at the Didymos system in 2026, will provide detailed analysis of the impact crater and ongoing surface changes. This extended debris emission was completely unprecedented and suggested asteroid impacts could have much longer-lasting effects than anyone realized. Surface secrets revealed. The impact revealed Dimorphos to be far more complex than a simple space rock. High-resolution images from the final moments before impact showed a surface covered in large boulders, some measuring several meters across, scattered across relatively smooth terrain. Olivier Barnouin from Johns Hopkins Applied Physics Laboratory analyzed the surface features and determined that Dimorphos likely formed from debris shed by the larger Didymos asteroid over thousands of years. The boulder distribution patterns suggested the moonlit surface was actively changing, with rocks gradually migrating toward the equatorial region due to Dimorphos's rotation. Patrick Michel, principal investigator for the upcoming Hera mission, noted that the impact site appeared to be in a region of relatively fine material between larger boulders, which may have contributed to the unexpectedly large momentum transfer. Spectroscopic analysis of the debris cloud revealed that Dimorphos has a composition similar to carbonaceous chondrite meteorites, suggesting it contains primitive materials from the early solar system. The asteroid's low density, approximately 1.17 grams per cubic centimeter, confirmed it was indeed a loose agglomeration of rocks and dust, with significant empty space between particles. This porosity explained why the impact was so much more effective than predicted. Asteroid defense revolution. The DART results revolutionized planetary defense strategies and demonstrated that deflecting potentially hazardous asteroids might be easier than previously thought. Lindley Johnson, NASA's planetary defense officer, announced that the mission's success validated kinetic impact as a viable technique for asteroid deflection. The unexpectedly large momentum change meant smaller, less expensive spacecraft could potentially deflect threatening asteroids with sufficient advance warning. Alan Harris from the Space Science Institute calculated that a DART-sized impactor could deflect most potentially hazardous asteroids if deployed years before predicted impact. However, the mission also revealed critical knowledge gaps about asteroid composition and structure that must be addressed for future defense missions. Amy Mainzer, principal investigator for NASA's Near-Earth Object Surveyor mission, emphasized that better characterization of asteroid properties would be essential for selecting appropriate deflection techniques. The DART success led to accelerated development of the NEO Surveyor Space Telescope, designed to discover and characterize potentially hazardous asteroids before they pose threats to Earth. ESA's Hera mission became even more critical, as it will provide detailed post-impact analysis necessary for planning future deflection missions. The success transformed asteroid defense from theoretical possibility to proven capability. The Hera investigation. ESA's Hera spacecraft, which launched in October 2024, represents the second phase of humanity's very first asteroid deflection experiment. Patrick Michel, the mission's principal investigator from Côte d'Azur Observatory, designed Hera to carry out a detailed forensic analysis of DART's impact effects. The spacecraft is set to arrive at the Didymos system in December 2026, and will spend about 6 months mapping both asteroids with honestly, unprecedented precision. Hera is equipped with advanced instruments including a laser altimeter, a thermal infrared spectrometer, and high-resolution cameras that can reveal surface features down to centimeter-scale resolution. The mission will also deploy 2 CubeSats, Juventus and Milani, to study the asteroid's internal structure using low-frequency radar and gravimetric analysis. Ian Carnelli, Hera's project manager, explained that the mission will measure the exact size and shape of DART's impact crater, determine how much mass was ejected, and analyze the ongoing surface changes. Hera will also investigate whether DART created a so-called moonquake that continues to affect Dimorphos's structure. This mission really stands out as an example of unprecedented international cooperation in planetary defense, combining European spacecraft technology with the analysis of an American impact experiment, all to benefit humanity as a whole. Unexpected discoveries. The DART mission, revealed phenomena that scientists never anticipated and are honestly still struggling to explain. Tony Farnham from the University of Maryland discovered that Dimorphos developed multiple debris tails that actually changed direction over time, suggesting there are some pretty complex dynamics happening within the Didymos system. Some of the debris seemed to be following orbital mechanics around Didymos, while other material was just escaping the system entirely. Fernando Moreno from the Institute of Astrophysics of Andalusia used computer modeling to show that solar radiation pressure was sculpting those debris tails into these really intricate patterns that could even be seen from Earth. The impact also appeared to have altered Dimorphos's rotation rate, though of course precise measurements will have to wait until Hera arrives. Masatoshi Hirabayashi from Auburn University proposed that the impact might have triggered landslides and surface restructuring that are still ongoing months after the collision. Spectroscopic analysis of the debris revealed water ice signatures, which was a big surprise given Dimorphos's location in the inner solar system. Simone Marchi from the Southwest Research Institute suggested the impact might have exposed subsurface materials that had been protected from solar heating until now. All these discoveries really showed that even a so-called simple kinetic impact can trigger cascading effects that fundamentally alter an asteroid's properties, behavior, and appearance for quite some time. Global implications. The DART mission's success, honestly, triggered worldwide investment in planetary defense capabilities and led to new international cooperation agreements. NASA announced plans for multiple follow-up missions, including advanced impactor designs and gravity tractor concepts for more precise control over asteroid trajectories. Meanwhile, China's National Space Administration revealed plans for their own asteroid deflection tests, and Japan's JAXA proposed missions that would combine sample return capabilities with deflection experiments. The United Nations Office for Outer Space Affairs began developing international protocols for planetary defense coordination, recognizing that asteroid threats really do affect all nations equally. ESA expanded their Space Situational Awareness program to include enhanced asteroid tracking capabilities. The mission's success also sparked private sector interest, with companies like SpaceX and Blue Origin proposing commercial asteroid deflection services. Brent Barbee from NASA. Goddard Space Flight Center is leading efforts to develop standardized mission planning tools that any space agency could use for asteroid deflection. DART's results were incorporated into updated planetary defense protocols, which are now shared through the International Asteroid Warning Network. Most significantly, the mission proved that humanity actually possesses the technology to protect Earth from asteroid threats, transforming planetary defense from science fiction into an operational capability that keeps evolving through international scientific collaboration. Future of planetary defense. The DART mission, honestly, marked the beginning of humanity's active role in solar system dynamics, with some pretty far-reaching implications for space exploration and planetary protection. Amy Mainzer's NEO Surveyor mission, launching in 2028, will use lessons from DART to better characterize potentially hazardous asteroids before deciding on deflection strategies. NASA is already developing advanced kinetic impactors with enhanced targeting systems and multiple impact capabilities for dealing with larger asteroids. ESA, on the other hand, plans follow-up missions to test gravity tractor techniques that could offer more precise trajectory control for sensitive deflection scenarios. The success of DART validated kinetic impact as humanity's first line of defense against asteroid threats. But it also made it clear that we need a better understanding of asteroid internal structure and composition. Organizers of the Planetary Defense Conference now use DART results as baseline data for impact deflection scenarios. The mission also established templates for international cooperation in planetary defense that go beyond political boundaries. Johns Hopkins Applied Physics Laboratory continues to analyze DART data to refine impact models and improve future mission designs. Most importantly, DART proved that with enough advance warning and international cooperation, humanity really can actively protect Earth from cosmic threats. The mission transformed us from passive observers of celestial mechanics to active participants capable of altering the trajectories of worlds. NASA hit an asteroid and wow, unleashed discoveries that are still reshaping our understanding of planetary defense. DART's impact on Dimorphos went way beyond expectations, proving that humanity can successfully deflect potentially hazardous asteroids, while revealing just how complex and dynamic these cosmic visitors really are. The mission showed that even small impacts can have massive results, transforming planetary defense from a theoretical possibility to a proven capability. With Hera arriving in 2026 to complete the investigation, we're stepping into a new era where humanity actually protects Earth from space threats. So, be sure to subscribe to Stellar Tech for more groundbreaking space discoveries that are defining our cosmic future. A rare visitor from deep space is currently flying through our solar system, and this one is mind-blowingly huge. 3I-ATLAS is barreling past at over 150,000 miles per hour and could stretch up to 12 miles across, making it the largest interstellar object ever detected. Unlike asteroids or comets born in our solar system, this cosmic wanderer originated from another star system entirely. But here's what has scientists both excited and concerned. 3I-ATLAS displays characteristics that don't match any natural object we've seen before. Could this massive visitor be something more than just space rock? A rare visitor from deep space. Deep in the cold emptiness between stars, objects drift for millions of years before occasionally entering our solar system as interstellar visitors. 3I-ATLAS represents only the third confirmed interstellar object ever detected, following the mysterious Oumuamua in 2017 and Comet 2I and Borisov in 2019. What makes this discovery extraordinary isn't just its rarity, but its unprecedented size and unusual characteristics that have astronomers scrambling to understand its true nature. The object's hyperbolic trajectory proves it originated outside our solar system, traveling through interstellar space for potentially millions of years before entering our cosmic neighborhood. Larry Deneau, principal investigator of the ATLAS Asteroid Survey, initially thought the detection was equipment error due to the object's enormous size and unusual brightness patterns. Unlike typical asteroids that reflect sunlight predictably, 3I-ATLAS shows irregular brightness variations suggesting either a highly elongated shape or surface features unlike anything in our solar system. The discovery has triggered an international observational campaign involving dozens of telescopes worldwide as astronomers race to gather data before the object disappears back into the darkness of interstellar space. This visitor may hold secrets about planetary formation in distant star systems and possibly answer questions about the prevalence of life in the universe.
The breaking discovery.
Tuesday, July 1st, 2025, marked a turning point in astronomy, when the automated ATLAS telescope system in Hawaii flagged an unusual moving object in its vast database of sky observations. Robert Warwick, the same astronomer who discovered Oumuamua, was monitoring the system when the computer algorithms detected something moving too fast to be a solar system object. Initial calculations suggested the object was following a hyperbolic trajectory, the telltale signature of an interstellar visitor passing through our cosmic neighborhood. The significance of this discovery cannot be overstated, as interstellar objects are extraordinarily rare, with astronomers estimating that only one passes within observable range every few years. 3I-ATLAS immediately became the most important astronomical target of 2025, with observatories worldwide redirecting their instruments to track this cosmic wanderer. The International Astronomical Union worked quickly to assign the official designation, marking it as the third confirmed interstellar object with the 3-1 prefix. Maria Womack, program director for NSF's astronomy division, called the discovery a once-in-a-generation opportunity to study material from another star system. the object's detection validated new automated survey systems designed to catch these fleeting visitors before they disappear forever into deep space.
The discovery story.
Late June 2025 began like any other observing period for the ATLAS asteroid survey, a system designed to detect potentially hazardous asteroids approaching Earth. The 4-telescope array across Hawaii and South Africa continuously scans the sky, taking images every few minutes and comparing them to identify moving objects. On June 28, the automated detection algorithms flagged an object with unusual motion characteristics in the constellation Lynx. Larry Deneau and his team initially dismissed it as a processing error, as the object appeared far too large and bright to be a typical asteroid at such distance. Confirmation observations using the Canada-France-Hawaii Telescope and Gemini Observatory revealed that the object was indeed real and moving at extraordinary speed. By July 3, enough observations had accumulated to calculate a precise orbit, confirming that 3I-ATLAS was following a hyperbolic path characteristic of interstellar objects. The Minor Planet Center in Cambridge, Massachusetts coordinated the global observational campaign, with telescopes from Chile to Australia contributing tracking data. Alan Fitzsimmons from Queen's University Belfast led spectroscopic observations that revealed the object's unusual surface composition, confirming it was unlike any known solar system body and validating its interstellar origin.
A stranger in our midst.
So, 3I-ATLAS really defies every expectation scientists had about interstellar objects thanks to its extraordinary size and mysterious properties. It's moving at about 150,000 miles per hour relative to the Sun, which is, way faster than any natural body born in our solar system could achieve without some kind of external acceleration. Davide Farnochia from NASA's Jet Propulsion Laboratory calculated that 3I-ATLAS measures between 6 to 12 miles across, making it potentially 100 times larger than Oumuamua and, honestly, the biggest interstellar visitor ever detected. The object's brightness varies dramatically over a 12-hour period, which suggests either an extremely elongated shape or maybe surface features that reflect light differently as it rotates. Unlike typical asteroids that maintain steady brightness, 3I-ATLAS shows magnitude variations of 2.5, indicating a highly irregular structure. The German Aerospace Center noted that the object's albedo, its reflectivity, is unusually high, suggesting a composition that's really different from most solar system bodies. Thermal infrared observations by the Spitzer Space Telescope detected no heat signature, which implies the object is either extremely reflective or made of materials with, pretty unusual thermal properties. But most puzzling of all is the object's trajectory, which shows slight deviations from pure gravitational motion, kind of similar to the mysterious acceleration exhibited by Oumuamua, but honestly on a much larger scale.
The predecessors.
The story of interstellar object discovery actually began on October 19, 2017, when Robert Warwick spotted Oumuamua using the Pan-STARRS telescope. This cigar-shaped visitor, measuring roughly 400 meters long, showed some pretty strange properties, including unexplained acceleration and an unusually high reflectivity that totally baffled scientists. Abraham Loeb from Harvard University even controversially suggested Oumuamua might be artificial technology from an extraterrestrial civilization, a hypothesis that, really divided the scientific community. Just 2 years later, amateur astronomer Gennady Borisov discovered 2I-Borisov from his observatory in Crimea, providing the second confirmed interstellar visitor. Unlike the mysterious Oumuamua, Comet Borisov behaved exactly as astronomers expected, developing a typical comet tail and showing predictable outgassing as it approached the Sun. Stefano Bagnulo from Queen's University Belfast led studies revealing that Borisov had a composition similar to comets from our own outer solar system, suggesting, similar formation processes across different star systems. The contrast between Oumuamua's anomalies and Borisov's normalcy really established a baseline for what interstellar objects should look like. Now 3I-ATLAS represents a third data point, and its unusual characteristics are once again challenging our understanding of what natural interstellar objects can be.
The cosmic journey.
3I-ATLAS entered our solar system from the direction of the constellation Lynx, following a trajectory that suggests it originated from the Vega star system, which is about 25 light-years away. Orbital dynamics specialist David Farnokia calculated that the object has been traveling through interstellar space for about 5 million years before entering our solar system in early 2025. The visitor's path will take it closest to the Sun in December 2025 at a distance of 0.7 astronomical units, so that's closer than Earth's orbit but not close enough to significantly heat its surface. 3I-ATLAS will pass within 50 million kilometers of Mars in November 2025, providing a unique opportunity for spacecraft observations using the Mars Reconnaissance Orbiter and the European Mars Express. After its solar encounter, the object will be gravitationally accelerated by the Sun's gravity, eventually reaching speeds exceeding 200,000 miles per hour as it exits our solar system toward the constellation Pegasus. The entire journey through our solar system will span about 18 months, with the object remaining visible to large telescopes until mid-2026. NASA's trajectory analysis indicates that 3I-ATLAS will never return, continuing its lonely journey through the galaxy for millions more years before, maybe, encountering another star system.
A scientific gold mine.
So, 3I-ATLAS, it's honestly a once-in-a-lifetime chance for scientists to examine untouched material from another star system. And, well, this time we've got modern astronomical tools that just weren't around during earlier interstellar encounters. James Green, who used to lead NASA's Planetary Science Division, actually described this discovery as the most scientifically valuable interstellar object we've ever found. And that's really because of its size, how close it is, and, the advanced technology we can use to study it. The James Webb Space Telescope, for example, has set aside 50 hours just to observe this object, using infrared spectroscopy to hopefully uncover the chemical fingerprints of the star system it came from. And Michelle Bannister, over at the University of Canterbury, is heading up an international team that's using the Atacama Large Millimeter Array to hunt for molecular signatures that might tell us more about where and how this thing formed. Now, unlike Oumuamua, which you probably remember faded out of sight pretty quickly, 3I-ATLAS is big enough that we can keep watching it for a much longer time and with several different instruments. Lucy Lim, a planetary scientist at NASA Goddard, pointed out that studying interstellar objects like this is really the only direct way we have to analyze material from other star systems, without, waiting centuries for an interstellar mission to get there. So, by looking at what this object is made of, we might learn whether the way planets form is pretty much the same everywhere, or if it changes a lot from one star system to another. And that could totally reshape our understanding of how exoplanets form and just how likely it is to find habitable worlds orbiting other stars.
Unanswered questions.
Despite months of intensive observation, 3I-ATLAS continues to puzzle scientists with anomalies that resist conventional explanation. Marco Michelli from the European Space Agency has detected slight non-gravitational acceleration, similar to Oumuamua, but without any visible outgassing or comet-like activity. The object's surface appears completely inert, showing no signs of water vapor, carbon monoxide, or dust emission despite approaching the Sun's heating zone. Thermal modeling by Alan Harris suggests the object's interior temperature should be sufficient to sublimate ice, yet no outgassing has been detected by even the most sensitive instruments. The object's unusual brightness variations remain unexplained, with some astronomers proposing it might be tumbling chaotically through space rather than rotating normally. Spectroscopic analysis by Vishnu Reddy from the University of Arizona revealed a surface composition unlike any known asteroid or comet class, showing spectral features that don't match meteorite samples or solar system objects. Most perplexing is the object's perfect preservation. After millions of years in interstellar space, it shows no signs of cosmic ray damage or space weathering that should have altered its surface. These mysteries have led some researchers to question whether 3I-ATLAS formed through natural processes or represents something more exotic than conventional astronomical objects.
The alien question.
The unusual properties of 3I-ATLAS have reignited debates about the possibility of artificial objects traveling between star systems. Abraham Loeb, who previously proposed that Oumuamua might be extraterrestrial technology, has examined 3I-ATLAS data and noted several characteristics consistent with manufactured rather than natural origins. The object's high reflectivity, unusual shape, and lack of outgassing despite solar heating mirror the properties expected from artificial materials designed for interstellar travel. SETI Institute scientist Seth Shostak acknowledged that while natural explanations should be preferred, the object's anomalies warrant serious consideration of alternative hypotheses. Loeb's analysis suggests that if 3I-ATLAS were a light sail or probe, its large size would allow it to maintain structural integrity during million-year journeys between stars. However, most astronomers favor exotic natural explanations, with Daryl Seligman from the University of Chicago proposing that the object might be composed of unusual materials like solid hydrogen or nitrogen ice that wouldn't outgas detectably. NASA's position remains that extraordinary claims require extraordinary evidence, but the agency has allocated additional observation time to gather more data. The debate highlights how little we understand about the diversity of objects that can form in other star systems and travel through interstellar space.
Observing the visitor.
3I-ATLAS has triggered the largest coordinated observational campaign in astronomical history, with over 100 telescopes worldwide contributing data to understand this mysterious visitor. NASA's Hubble Space Telescope provides high-resolution imaging capable of detecting surface features, while the James Webb Space Telescope analyzes infrared signatures that reveal composition and temperature. Ground-based observatories including Keck, Gemini, and the Very Large Telescope conduct continuous monitoring to track brightness variations and search for outgassing signatures. Radio telescopes led by the Green Bank Observatory and Arecibo successor facilities listen for any artificial signals, though none have been detected. Planetary radar systems at Goldstone and Arecibo attempt to map the object's shape and rotation, but its distance pushes the limits of current radar technology. Amateur astronomers worldwide contribute observations using increasingly sophisticated equipment, with citizen science projects analyzing thousands of images for subtle changes. ESA's Gaia spacecraft provides precise astrometry measurements crucial for tracking the object's trajectory and detecting any acceleration anomalies. The Spitzer Space Telescope, despite being retired, was briefly reactivated specifically to observe 3I-ATLAS using its infrared capabilities. This unprecedented global effort demonstrates how rare interstellar visitors unite the astronomical community in pursuit of understanding our cosmic neighborhood. 3I-ATLAS continues its journey through our solar system, carrying secrets from another world that may never be fully revealed. Whether it's an exotic natural object or something more extraordinary, this massive visitor has already revolutionized our understanding of what travels between the stars. As we develop better technology to detect and study these cosmic wanderers, each new discovery brings us closer to understanding our place in the galaxy. Subscribe to Stellar Tech for more groundbreaking discoveries that challenge everything we thought we knew about the universe and our cosmic neighborhood.